All right, so as I said, one thing we're going to take a little bit of a digression today and talk about number two from your assignment that was due this last weekend. DFS, just to recap what it is, DFS can be used to determine if two vertices x and y are connected in a graph, right? You can go from x, is there a path from x to y? Or in an undirected graph, y to x, it's the same thing, right? Develop an algorithm, or DFS can also be used to determine if a graph contains a cycle or not, right? That's pretty straightforward. The ones that we talked about in class were found any cycle though, right? What we want is a very particular type of cycle. Develop an algorithm by either using or modifying DFS that, given a graph G and two vertices x and y, determines if x and y are connected by a cycle or not. So in other words, what we mean by that is a graph where we've got, say, x and y, and there is a cycle connecting them. So there's some path P1 from x to y and another path P2 that is disjoint from the first path, right? That forms a cycle like this, okay? So for example, if we have like a complete graph here and there's x and there's y, well, clearly they lie on a path right here, or they clearly lie on a cycle right here. But that it could be a different graph. It could be like a graph that, say, is like this, where I've got y over here. Now, there's one path from x to y. That should be clear. But there's not another path from x to y that would form a cycle, right? You could have this path, and then you could find this path, but that doesn't form a simple cycle, right? So you do have to be careful on this. So what I want to do is I want to first write out the expected pseudocode, or what we were thinking about when we were thinking people would write up the pseudocode. So for example, let's go ahead and just go identify our input here. A graph, G, and two vertices, x and y, in the vertex set, B. Let me go ahead and give myself some more room here and identify that G is the vertex set and the edge set, with x and y being in those in the vertex set. All right? And my output here, we could say we would output the cycle, or we could say that, just making sure that this works, or we could say that we're simply going to output true or false. Yeah, okay, everything's working. All right, let's go ahead and put output true if x and y lie on some cycle. Now there could be it could be the case that x and y lie on a million different cycles, right? We're just interested on whether or not they lie on at least one cycle. Okay. So here's my pseudocode. For example, let's suppose that we have access to this other subroutine called find a path, G, X, and Y. And we'll come back to this, but this could be formulated as a subroutine. In other words, this right here is just DFS, right? Find a path from X and Y from X to Y, right? Now, if there is no such path, right? Say that our placeholder for this was phi or none or something like that, then I'll output false. Because if there's not even one path between X and Y, how can there be a cycle? Otherwise, what I'm going to do is I'm going to formulate G prime, which is equal to G minus the path P1. And I'm just going to go ahead and put this in as a descriptor in my comments, right? This is G with all edges in P1 removed. We don't want to remove the vertices, right? Because if I want to find another path from X to Y somewhere, right? If I remove that vertex, then it's gone. Another solution that we saw was remove only one edge, right? So like remove this edge right here, right? And that's not the case either, because you could have, say, X what goes out to this edge, and then it follows some path over here to Y, right? And then by simply removing this one edge here, you could find another edge that then rejoin this path right here, right? And that there was not actually a cycle, right? So you can't just remove one edge. You have to remove the entire path along the path that you found, right?
So once you've removed that, then you ask the same question again. P2, we'll go ahead and call find path on G, X, and Y, right? G prime, excuse me, the new one, right? And if P2 is null, or none, or V, or whatever, then output false. False. Otherwise, output. And what you can do is you can output the path, the actual cycle, right, by combining those two paths into one, or true, right? It all depends on how you design the function. Do you want this function to output true or false, or do you want this to be a functional version of the problem where you're actually outputting the actual cycle that you found, okay? What does find path look like? It's just a straight up DFS, right? So find path would look maybe something like this. G, X, and Y, where you start, I don't know, you start at X, so color all vertices white, unvisited. Then you color X, dot color, you color that gray. And then you NQ it, so S is going to be a, not NQ, a stack. Yep, you push it. S dot push X, excuse me. And then you go into a regular old while loop, right? While S is not empty. I'm just going to modify the DFS that we gave. I'm going to cut out all of the extraneous stuff that you're not actually going to use. The discovery times, the finish times, etc. Right? So what I'm going to do is I'm going to look at what's on top of this stack, right? Using S dot peak. This is the current vertex. Now, if the current vertex is equal to your end vertex, the thing that you're looking for, you're done. You found a path. Output the stack. That's what's representing your path, right? Those are your breadcrumbs. Your stack is, I started at this vertex, I went to this vertex, I went to this vertex, I went to this vertex. That's the path that you've followed so far. When you back up, when you backtrack, right, you're popping stuff off of that stack, and you know you're stepping backwards instead. And so the stack represents the path that you want, right? If you found Y, then you're good, you're done, right? Otherwise, say if the neighborhood of U has unvisited, visited white vertices, right? Then just select one of them, right? V will be the next white vertex. Okay? And then color it gray. Color V gray. And push it. S dot push U. There we go. Otherwise, if there are no other white vertices, what do? Else? Well, you've reached a dead end, right? Everything behind you is either black or gray or something like that. Now you need to backtrack. Backtrack. By S dot pop, right? And you don't need to save it because you already have U. That's the current vertex, right? And that's the end of your else, right? Otherwise, output phi. Now, if you ever find a path, you'll end up outputting it right here. If there is no such path, you'll end up doing a complete DFS, starting at X and not starting over. Don't start over, because if Y is in a completely different connected component, then there's no path, and you would output phi. Okay? So this find path here is basically just DFS. It would end up being order M plus N. How many times do you do it? Once? Twice? So this entire thing would end up being order 2M plus N, which is order M plus N, or you could simplify that to order N squared. Right. Okay. I thought it would be a good idea to, or I don't know, questions on this before we move on? Yeah, go ahead. Okay, good.
During the DFS search tree,
All right, so which one?
when we go I, A, and F, E,
Mm,
normally tell us the DFS.
like an actual graph that I brought up or that I
Yeah.
drew or what?
You brought up.
Graphs. This one?
Yeah.
Okay.
So I wanted to see if you can find between like I and H has a cycle.
I and H.
Uh huh.
All right, and there's definitely a cycle.
Uh huh. But then
Okay.
I think it because like when I get you go I, A, B, C, D,
I, A, B, C, D.
and then F, E doesn't work, E, F doesn't work, so you go G, H.
Okay. So,
So you go
like
G,
this?
H. And then if you remove that, because A is gone, I think you can't have another path.
No. So, you want to remove all these red vertices.
Uh-huh.
Is that correct?
No, I, A, B, A goes to B, and then B goes to C, and C goes to D.
Ooh. Wait, which one?
I goes to A, and A goes to B,
I goes to A goes to B.
B goes to C,
Okay.
C goes to D, D goes to G, G goes to H.
Okay.
And then if you remove all that,
All right, let's go. So, suppose that those are all removed. Then you would try it I again. Here you only have one choice. Okay. Here you have two choices.
both leads to D.
So okay, D. All right, we'll go with that. And now you only have one choice again. Go to B. Ooh, yeah. Did you find a counterexample for this? Damn.
Because like any algorithm I try, I can get I think to H.
Maybe it's not as simple as that. That's a good one. That's a good counterexample. Can you see so I and H? You may end up taking out edges that are superfluous edges that are not necessary. So do you have to do shortest distance? Because if you another way of doing it, so maybe adding on this other condition. So if you do DFS, or let's say BFS, all right, because that on an undirected, unweighted graph, that gives you the shortest distance path. Okay, so if you do a BFS and you find it and you take it out, then you're taking out the shortest path. Then there has to be at least another next shortest path. And would you necessarily be taking out? So here's one path. Here's another path that joins up and shares this path over here and then comes back over here, X and Y, right? But then you ended up taking this out. This is a generalization of what you're pointing out here, that you end up taking out this essential edge.
Well, is X and Y did it make a cycle?
So suppose one DFS goes like this. What you've done is you've taken out all the edges necessary to find the other path. I think you can. I'd have to come up with a proof, but I think that you can fix this by saying that you need to find the shortest path. Because if you find the shortest path and another shortest path, well, no. Let's come up with a counterexample for that. All right. Here's X and Y. X going to Y, there are two shortest paths, but they're of the same weight. Okay. Now, no, you'd find it. Wow. I think that will work, but I'm not sure. In any case, damn. I've only graded like 3 out of the 4 so far, but I think you just threw this question out. Now, well, that saves me having to grade the other 4, but it means I have to go back to the other 3 and just throw them out. Throw them out as in like awarding all the points no matter what. This is really good. This is really interesting. This was the intended solution here. You find one path and then you need to find another after removing it. I mean that seems to make sense, but this is an excellent counterexample.
Why is it? Because so like for example, the graph you drew there, is that a cycle? Does it make a cycle? Is x y in a cycle in that case?
Well, yeah, sure, certainly. Right. Here's the cycle for I and H. Right. Here's a cycle involving I and H. Right. Here's another cycle involving. So here. Nope. There's no other cycle there.
Only one cycle.
I think so. Yeah. Because you have to come out and then get to I somehow. But this is a bottleneck right here, so you can only go that way on that one and that way on that one. So there's only one cycle.
And A is also a bottleneck.
Yeah. Well, A is not a bottleneck because you can go like this, but then, yeah, in that sense, it's a bottleneck. Yeah. What is the property that is leading this to a counterexample that we can then overcome? 1, 2, 3, 4, 5, 6. But then the shortest path is 1, 2. And then that means that there's 1, 2, 3. There are several paths remaining over to I that you could find.
I think it's like D and A as a bottleneck.
So D and A. And you end up getting both bottlenecks in your first path here.
Because you have to go minimum on the DFS search. You have to go minimum.
Yeah, if you went BFS on this, well, I'm not even sure that that's true anymore. But let's go ahead and try it. There, you found the shortest path 2. Now you would necessarily find the other path if you did BFS again. Shortest path, shortest path. Can we come up with a counterexample where there are 2 shortest paths? So in other words, they're the same length, but they have the property that they go through the one of them takes both bottlenecks, right? So X, somehow these are the bottlenecks, and then it gets over to Y. And you need one of those bottlenecks to actually get over here. A, B, C.
Low and bottom.
Yeah, 1, 2, 3. But then there's a shortest path here. So let's eliminate that. A, B, C, D. So now 1, 2, 3. 1, 2, 3, 1, 2, 3. But if my DFS ends up being like this, or my BFS ends up being like this, and I end up, there's a counterexample right there, right?
If that's shortest path.
1, 2. I mean, the shortest path from X to Y is always going to be 1, 2, 3. And if your DFS or BFS, through whatever criteria you're using, happens to find this, then what are you left with? You're left with a disconnected graph. You wouldn't even get the correct answer at that point. Well, you'd say, no, there is no cycle, right? When there clearly is, right there, like that. Because the second call in this idea right here would say there is no second path. But that's by virtue of you having taken out these two bottlenecks. This is now a Gomer question. To come up with a counterexample, either this one or the one that we just came up with right here. That it's not even sufficient to say that you can find the shortest path at all. Damn. All right. Well, that kills the rest of my demo. What I was going to do, I was going to actually program it in Network X, but no, not anymore.
Is there like has somebody implemented this? Like find a cycle?
Well, I mean, certainly you can find a cycle, right? That should be straightforward, just DFS.
Or has somebody implemented like F2 versus?
That's a good question. That's what I was about to Google here. Find. How should I even formulate the question? Determine if two vertices are on a cycle or not. Directed graph. I'm sure that we can find. Yeah. Non-empty path. You have a site is similar. Let's imagine a directed graph with two vertices. That's not. What kind of question is this? All right, I don't even. It's not asking for the algorithm. How to find which vertices are in a graph cycle? Okay. Check the existence of a cycling graph with only number. No. Okay, maybe that one. Determine if a vertex is part of a cycle. Directed graph G, directed by the adjacent, blah, blah, blah. True if F is part of a cycle or not. Strongly connected, yeah. Certainly, you could just run straight up DFS on that, right? Because you could say that instead of coming back on any particular, gray vertex, do you ever come back to the one that you started with? So you can certainly do it with one. How do you do it with two, though? This is an excellent question. A terrible answer that I had, or that I was expecting, but... All right. I'm finding if there is a path between two vertices now. Path, is there an undirected graph? Only have two vertices. So directed, it should be pretty straightforward, right? Because if you find a directed graph, or if you find a directed path from X to Y, and you take that out, right? It doesn't matter if you take that out or not, right? None of those vertices will, or none of those edges will be shared on the path back to X, right? So a directed graph, it's pretty clear. So just convert the undirected graph into a, you can't do that. What I was going to think was take the undirected graph and simply just add, two edges back and forth. But then that doesn't even detect a cycle, because there could be a path here and then the path back is exactly the same. Yeah. Do you have an idea? Or?
I'm trying to draw the directed graph. So why is it easy on a directed graph?
Here. Because if you find a directed path from X to Y, we're not going to have the same problem taking it out, right? That to form a directed cycle, you have to have a direction back, and none of these, all of these are oriented this way, so you're not going to be able to take any of these backwards on this path right here.
Even if it goes to the exact same vertices, as long as
Well, then that begs the question too, like, because you could have something like this, right? And it's ill-defined, right? Because now here's your cycle, right? That's not really a simple cycle in my book. So maybe it's not as easy on a directed graph either. We could go the other way of thinking, and this is what we're going to introduce after dynamic programming, is computational complexity, NP completeness, and proving that particular problems are extremely difficult through reductions. Like, if you had a solution to this problem, would you then be able to trivially solve this really, really difficult problem that nobody knows how to solve? So the other way of thinking here would be, what if you could say that that you could solve that problem? That you could say that X and Y lie on some cycle. Now, could you use some sort of a graph gadget to solve, say, a Hamiltonian path? Or a Hamiltonian cycle? Right. And you may be able to, actually. How? No, I don't think so. At least not immediately. Damn it. I don't know if I want to think about this anymore. Yeah, during class at least. And it kind of killed you killed the mood, man. I was going to show you, I just threw this together right beforehand. I'll just show it really quick. There's the implementation for find path, right? And that definitely works. And then here's my implementation of on cycle. I was going to take the opportunity to point out that you can use, things like, where is it? Here, this. Unvisited vertices. I want to know what all the, I want to get the neighborhood, but I only want the unvisited vertices in the neighborhood. You can use a list comprehension for that very, very easily, right?
State? What is that?
Oh, that's just what I did. The state, I initialize everything to unvisited white.
Oh.
Right? It's just a map,
Oh.
right? And then I made X to be visited. That's where I started. And then for all vertices in the neighborhood of U, if it's unvisited, then include it in this list so that you can say, well, if that list is empty, then backtrack by popping. Otherwise, move forward by simply just taking the first one.
Is that used in attributes? In
You can use attributes too, yeah.
I think you can't use list comprehension as well.
You may or may not do. Yeah, it might just be iterable or something like that. I don't know. But then here's my on cycle. I just used Network X's functionality. All right, if there's a path from X to Y, well, if there's no path, then there's no cycle, so false. Otherwise, I get the path from all simple paths, and then I create G without the path, which is a deep copy, but then I go through and remove all those edges in that path. And then I ask the same question, does it have a path from X to Y in G without that path? But as we've already seen, we've got a counterexample. Nope. All right, so like I said, I'm going to go back. I've only graded 3 or 4 already. The ones that are not yet graded will just be automatic points. The ones that are graded, I'll go back and restore those points. What was your idea, if you want to share?
The more I thought about it, there's like, I think there's like something to it, but it's probably constant, which is basically like, you doing DFS,
Okay.
when you get to the point where you're considering like the next path to take, so you'd start from X,
All right.
like no matter what, so you guarantee it's a, if you ever get the chance to go to Y, you do it, like you put Y into the stack.
All right. I see Y right here going from A. Okay.
Yeah, so if you're at A, you necessarily get Y.
Okay.
And then you just continue DFS, and if you ever have a chance to return to X, you go around the same cycle. And if you're never given that chance, it would not.
I like that.
Problem that I see with it is that like, I think you can still have issues where you take a path that can block something off, but I'm not sure.
So, yeah, maybe this one right here. So just by chance, I go over here. I do have a chance to go over to Y, but then I'm stuck in that dead end.
So it probably becomes a secondary issue. I don't know.
So there's another Gomer. I like this counterexample. It's proven us both wrong, right? Well, this one proved the original wrong. This one proved the shortest path wrong and the preference for Y strategy wrong.
Is it possible to kind of like combine those two solutions? Like if you, like the first one, you have a chance to go, I gotta go there. So then you get X, A, Y, and then just like terminate there, delete those edges.
Oh, okay. Well, still, if I just happened to go to C first and said, like, or lexicographic order, say that this is A and this is C instead, right?
Yeah.
I end up, I have no choice. I have no, starting out, I have no preference to go to either one of these things. And so you can always be adversarial and say, if lexicographically, we'll go to the one that's going to kill the algorithm, right? Come over here. Oh, now we have a opportunity to go to Y. Remove that, and then we're back over here to our disconnected graph, right, where we can't get back to X at all. Yeah.
What if you don't just run at random order and then run it like enough
Yeah. Yeah, you could brute force it like that. Sure, certainly. Find all paths from X to Y. I mean, that's what Network X does. Oh, by the way, I shouldn't have deleted it, but you should really read the the documentation for this, right? Because I was amazed that they even implemented this. This is basically what you did in your first assignment with Hamiltonian path or Hamiltonian cycle or something like that, where you're finding all simple paths. Well, all of them, period, with a particular source and a particular target here. In fact, I think that those are optional. You can find all simple paths, period. Now, that's obviously going to be super exponential. And the documentation even says that. So you might be wondering, well, wait a second, if you called this on like a large enough graph, isn't it just going to sit there and hang? And no, the reason is that this is iterable. So it doesn't build all the paths at once. It builds a path, and then when you ask for it, here you go, right? Then if you ask for another one, it builds it and gives it to you. So it doesn't build all order n factorial paths. It builds one at a time. If you were to iterate through all this, oh yeah, then that's, in fact, we could show you. Let me go ahead and give me here's a complete graph on 6 vertices, right? And get rid of that. All simple paths, doesn't really matter. From 0 to 5, right? There we go. 4, P in, hopefully it's printable, print P. Let's find out. Python on cycle. Nope, NX is, oh, sorry. I didn't bring in Network X. So let me bring that in now. Hopefully it's installed still. Yep, I've not rebuilt it. There we go. So there's assignment 1, right? Just in one liner that you're using this. Of course, we would not have allowed you to use that, right? But I can go ahead and pump this up to, I don't know, 100 vertices. And now is this going to execute within our lifetime? Well, I mean, it will continue executing for our entire lifetimes, right? But no, there are way too many. 100 factorial, or 2 to the 100, yeah, 100 factorial or something. No, that will never work. But it runs because you're only asking for one at a time.
Solve the algorithm problem. You want to give it now.
Yeah, but it's not in the way that you want to. Network X. All right, all simple paths. Again, it was a very interesting documentation. I don't know why they even did this. Right? Yeah, there we go. It finds one in order v plus e time because it uses DFS. But the number of simple paths in the graph can be very large. Example, n factorial. So this does not check a blah, blah, blah. So you don't actually want to use this to generate all the paths. Right? And then dump them to some file or something because that's astronomical.
So for your Network X, you just used a map to like keep the
Oh yeah,
visible.
for the states.
I made like a class.
Oh,
And Network X does not like classes as like the nodes. It's not that necessarily
I can see
itself,
that, yeah.
It's just very difficult to like parse.
yeah.
You kept talking about node object at location.
Right. The other alternative would be to use the attributes. What's the syntax since you did it?
G dot node.
Q dot. Oh well, like just a particular node U
Okay.
here.
And then you do another bracket.
Okay, then
You can call that
visited or visit or color, let's say,
yeah, color. And then
Right.
yeah, equals.
equals black, white, whatever. Right. Yeah, you could have done it that way too.
Yeah, in mine, I made like a class and I used those as the nodes.
A node of a node of a node.
It got like super difficult to understand.
Yeah, I mean, I my go-to is just always quick and dirty map. Be done with it. Yeah, and that's what the handout, or that's what our formatting was. It's just 0 through n minus 1. That's the default for most things. Like this is 0 to 99. That's why I'm going 0 to 99 here. Even just 100 or 10. 10 factorial is what? Yeah, still too many. We haven't even gotten past 0 as the initial vertex here. Okay, there we go. No, that's right. We went to 0 to 9. And that's not even all of them, right? That's only the ones starting at 0 and ending in 9. So bad. All right, so short answer, I'm going to revisit that one. If somebody comes up with another answer, please let me know. Otherwise, I'm going to research that myself. What I want to do with the remainder of our time here is just to simply introduce the next algorithm. To do that, I want this graph right here. Okay. So what we're interested now in is a shortest path algorithms. So we've gone through. Does there exist a path? Right? Does there exist or what's the minimum spanning tree? Now we're going to combine that into I want all paths. Right. So starting at a vertex, say V, find all shortest paths V to all other vertices W, right? For all W. So let's just go ahead and start at an arbitrary vertex here. Where do you want to start, first of all? Well, okay. Let's not start trivially at A here. Right? This is a directed graph. Are there any outgoing vertices? No, we're pretty much done at that point, right? We would say though that there is a path from say A to F, right? Its weight is going to be infinite though. So that's the way that you say that there is a path. It's just of infinite weight. In other words, there is no path. All right. So give me another vertex that's not so trivial. You could go with B, but that's only slightly less trivial. Why? We only have one edge outward, in which case we're done because now there's no other way to get anywhere else, right? So there, everything else would then be an infinite weight. Okay. I would go out. Yeah. Well, no, you could get pretty far, right? You could go from I to G to F to C and A. You could also go anywhere else. Well, there too, right? But that's pretty much it. E. All right, let's go ahead and go with E. I like that. All right. So now the idea here is exactly like Prim's algorithm. What we're going to do is we're going to start at that vertex, and then we're going to go outwards to everything that is emanating from this, and we're going to say, oh, well, wait. Now we can get to B, D, and G at a cost of 5, 5, and 20 respectively. If we ever find another path that's less, then what we're going to do is we're going to update those, and so we need to keep track of three things. We need to keep track of the weight, the predecessor vertex, how we got there, right, and the vertex itself, right? So what I mean by that is let's go ahead and start out with initializing everything, right? So there is no predecessor vertex, and it's an infinite weight, B, C, D, E, F, G, H, I, J. Wait, did we go too far? No, that's it, right? That's everything, right? And initially, I don't see anything, right? There we go. Now, if I'm going to start at E, what I do is I initialize E here, right? And I'm going to take that out of contention, okay? And I'm going to say, well, if I'm starting at E, there is no predecessor vertex, but how much weight do I need to expend, or what's my cost of getting there? Well, if you start there, there is no cost, so 0. Okay. Now what I do is I look at the neighborhood, the outgoing neighborhood of E, right? And I can see B, D, and G. Let's just look at B first of all. Right? I can get there from E at a cost of 5. Is that better than infinite? Certainly. So I'm going to go ahead and update that. I can get there at a cost of 5 by going from E. Going from E at a cost of 5. All right, so this is the vertex. This is the predecessor. And this is the weight. Okay. I can also get to D at a cost of 5, which is better than infinite. So going from E at a cost of 5 gets updated. Likewise, G gets updated at a cost of 20 from E. Okay? Now, on my next iteration, what I'm going to do is I'm going to I can see these three things right now, right? I'm going to select the minimum distance one here. Breaking ties arbitrarily. So I'll go ahead and break ties lexigraphically here, right? And I mean by weight right here, right? So some of these are infinite and I'm not even going to consider them. But this one and this one are minimal, so I'm going to go ahead and break this one out over here. Now, that's equivalent to taking this edge right here and fixing this vertex, kind of like prims, right? With prims, we emanated outwards, taking edges, edges. But our criteria is different. Instead of trying to minimize the entire tree, we're trying to minimize the path with respect to this source vertex, E. Okay? Otherwise, it is exactly the same. Look at its neighborhood. I can get to A at a cost of 7. Is that better than infinite? Yep. But my predecessor is B. What is the cost to get there, though? It's not just 7, right? There was a cost to go from E to B, 5. So if I'm going to go from E to B to A, I need to add up all of the costs along the way. And this is going to end up being 12. Okay? Yeah.
So when you say it's a greedy solution, is this what it means?
You're being greedy about it. Yeah. Yes, this is the greedy one. Yep.
So you it means you want to have net.
Yeah, you're making locally optimal choices, which leads to a globally optimal solution, right? One way of typically visualizing this is say like a, there we go, right? So there. This is representing some function, right? And you're trying to find the minimum, right? Well, if you only consider, say, a local scope, right? You're only looking between these two right here, right? What's the best solution? What's the minimum solution? It would be whatever this critical point is right here, right? But is that the best you can do? Nope. There's one even over here that's lesser. So if you're only for a lot of problems, if you're limiting your consideration to a local scope, you'll get a locally optimal solution, but you may not necessarily get a globally optimal solution, right? In which case, you have to basically force yourself to get up over this hump and then look at this globally minimum solution or globally optimal solution. There are problems where your minimum choice property, it's minimum choice property or something like that, where you can prove mathematically that your minimum choice, your locally optimal solution, leads to a globally optimal solution. And there are problems where being greedy does not lead to you can prove with a counterexample, you can prove that a locally optimal choice does not lead to a globally optimal solution. Knapsack, for example. We'll look at that again when we look at the dynamic programming solution for it. But yeah.
Can't be greedy on that. So.
Yeah, you can't. Yeah, I mean, you can, and it'll give you an answer. It'll give you a good enough answer, but not necessarily an optimal answer. Right? That's what heuristics are all about. Right? Fast forward. We'll probably have to pick this up next time, but fast forward through this a little bit more. And what do we have next? DE5. That leads to me going to D at a cost of 5, integrating that vertex and fixing it. And then I look at its neighborhood, right? Now remember, it cost me 5 to get here. So, yeah, I'm looking, yeah, and G, so, yep. Now B, I don't consider that because I've already pulled it out of whatever data structure I'm using over here. By the way, guess what kind of data structure are we going to be using? A heap, exactly, right? Or a priority queue. So I'm not going to consider B again, but I will consider A here. Hey, it took me 5 plus 5 to get to A. Is that better than going through B? Yep. So we update it to be 10, and instead of going through B, we go through D instead. Okay? The next thing I look at is C. Well, anything is going to be better than infinite, so I'll update this to D. Oops. D at a cost of 25. Why 25? It cost me 5 to get to D. It cost me another 20 to get to C for a total of 25. F is likewise. That's D and 25. And G, I can get there at a cost of what now? 5 plus 10, 15. Is that better than 20? Yep, so that gets updated. D and, what did I say, 15? There we go. Next iteration of this algorithm, what do I pull out? A to D. And so I am fixing this edge right here and incorporating A. But is there anything to consider in its outgoing neighborhood? Nope. So I continue. I pull out this one. D to G, or D to G, excuse me, incorporating G. Its outgoing neighborhood is F and I. What about F? What did it cost me to get here? 15. It cost me another 10 to get to F for a total of 25. Is that better than what we found so far? Nope, so we don't update it. Right. You can break tries arbitrarily there as well if you want to. The other one is going to be 5 out of I. Again, it cost me 15 to get here, another 5 to go to I, so for a total of 20. Is that better or worse than, well, infinite? What is it going to be, 20? And you came from G. Right. Next iteration, what do I pull out? The one that I just discovered. And there we go. I look at its neighborhood, and one of those things is already pulled out of the consideration. The other one is going to F at a cost of 5. Remember, it cost me 20 to get here, though. So 20 plus 5, 25 is no better than what I've found so far. Okay. Fast forwarding here, what would it look like? You would pull out C, right? And that would be done. You don't update anything else. You would pull out F from D. Wouldn't look at anything else. And what about those other two things? Yeah, you'd pull them out because they're infinite and they're in your heap. So you'd pull it out, but then then you'd update the neighborhood, but you would end up not updating anything here. I guess you'd update J when you pulled out H, but infinity plus 10 is what? Infinity. So you would end up with these two saying that these are unreachable in your algorithm. Right? This is known as Dijkstra's algorithm. Dijkstra's. Right. And it gives you the shortest path from a single source, in this case E, to every other vertex. What if you wanted it from G instead? You'd have to run the algorithm starting at G as your source. Right? Or you'd have to run another algorithm that we'll look at on Wednesday after we've codified this, called the Floyd-Warshall algorithm, or Floyd's algorithm. Right?
It's Dijkstra. 'cause
Dijkstra?
in Witcher,
Wait, what?
Dijkstra, they call him Sigmund Dijkstra.
Is this the TV show or is it?
Witcher, the video game.
Oh, okay.
The Spy Master. Dijkstra.
Dijkstra? Really? Dijkstra? Okay, we got 3 pronunciations. All right.
Yeah, Sigmund Dijkstra.
Okay. This is Edgar Dijkstra, so I've always said Dijkstra or something. Consult an online name pronunciation audio version of it and find out what it sounds like. Otherwise, if you again, I'm still in the process of grading, and those will be updated. If you do find a solution, please go ahead and send it my way.